All right, let's jump right in. We're about to explore a technology that is, and I mean this literally, shrinking entire medical laboratories down to the size of a credit card. Now, I know that sounds like something straight out of science fiction, but it's very real, it's happening right now, and believe me, it's about to change just about everything you think you know about healthcare.
Just let that sink in for a moment. Imagine a full workup, blood counts, checking your metabolism, screening for diseases, all from one single drop of blood. No more armfuls of vials, no more agonizing waits for results. This is the incredible promise we're talking about today. This isn't just a small step forward, it's a giant leap.
So, you're probably asking, how on earth is any of this possible? Well, to get the how, we've got to shrink ourselves down. We need to step into the micro world, a place where the normal rules of physics, they just don't apply. Things get strange and really, really powerful.
So what is microfluidics really? At its heart, it's the science of controlling teeny, tiny amounts of liquid. We're talking about channels so small that a single strand of your hair would look like a superhighway next to them. And it's at this scale, this micro level, that the physical world starts to behave in some very cool and useful ways.
See, in our big world, gravity is the boss. Drop some water and it splashes. It's chaotic. But down in the micro world, gravity barely matters. Instead, surface tension is king. Fluids stop acting like water and start behaving more like honey. Everything flows in a smooth, predictable, and perfectly controllable way.
And here is the number that makes it all work: 20,000. At this tiny scale, the surface area of a liquid, compared to its volume, skyrockets by a factor of 20,000. Now, why should you care? Because all the important stuff in chemistry, the reactions, it all happens on the surface. More surface area means reactions that once took hours can now happen in a matter of seconds. It's a massive speed boost.
And all of this leads to the secret sauce, something called laminar flow. It just means there's zero turbulence, no chaos. The flow is so smooth and predictable that you can actually run two different liquids side by side in the same channel and they won't mix. It's like they have invisible walls between them, giving scientists total control.
Okay, so the physics is pretty mind-bending. But how do you actually build something with channels thinner than a human hair? It's not like you can just get out a tiny power drill. The manufacturing process, it turns out, is surprisingly clever and, well, elegant. The whole thing is based on a process called soft lithography. And honestly, it's a lot like making a fancy Jell-O mold. First, designers use light to etch a master template with all the tiny channels. Then, they pour a clear, rubbery polymer over it. After it sets, they just peel that layer off, bond it to a simple glass slide, and boom, you've got yourself a sealed, ready-to-use lab-on-a-chip.
And they use the specific polymer, PDMS, for a few really good reasons. For one, it's totally clear, so you can literally watch the experiment happen. It's also biocompatible, so it won't harm biological samples like your blood. And, get this, it actually lets gas pass through, which means living cells can stay alive and breathe right there on the chip. It's pretty much the perfect stuff for the job.
All right, we've got the weird physics, we've got the clever manufacturing, but that all leads us to the most important question of all. So what? Why does this matter? Well, let's look at how this tiny tech is sparking a massive revolution in medicine.
I mean, just look at this contrast. The old way, the way we've done it for decades, is vials of blood sent to a big central lab where you wait and wait. The new way? A single drop of blood, tested right there in the clinic or doctor's office. Results in minutes, not days. And for pennies, not hundreds of dollars. This isn't just an upgrade, it's a total game changer for the patient. And while it's being used everywhere, its biggest splash is definitely in diagnostics. That's about half of the entire field right there. But it's also making a huge difference in drug development, helping find new medicines faster and cheaper. And it's giving researchers in the lab powerful new tools to understand the fundamental building blocks of disease.
And these breakthroughs aren't just theoretical, they're happening now. We're seeing disease detection that's literally 1,000 times more sensitive than old methods. Those PCR tests we all got to know so well, their time is being cut from hours down to minutes. And maybe most incredible of all, these chips can sift through billions of healthy blood cells to find and isolate one single rare cancer cell. It's astonishing.
So let's bring it back to you. What does all of this actually mean for your health? Let's zoom out and see how this tech is completely rewriting the timeline of our personal healthcare.
If you think about it, in the past, medical testing was slow, clunky, and centralized. Right now, we're in the point-of-care era, where these devices are showing up in your local clinic and ER.
But the future, where this is all heading, is continuous health monitoring. Imagine a world where your health isn't just a snapshot from your yearly physical, but a constant, real-time movie of what's happening inside your body.
And that is the ultimate goal. That's the end game here. When you have that much data, that much insight, medicine is no longer a one-size-fits-all guessing game. Treatments, medications, even diet and exercise advice can be perfectly tailored to your unique body in real time. Personalized medicine finally stops being a buzzword and actually becomes a reality.
So I'll leave you with this to think about. When we reach the point where your doctor can run dozens of tests in minutes, all from a single drop of blood, the whole conversation changes. The question is no longer, what can we afford to test for, or what do we have time for? The question becomes, what do we want to know? It's a tiny technology, for sure, but its implications for our lives are absolutely massive.